All right. Welcome to episode 41 of the Jake Blanchard podcast, brought to you in part by our friends at Fellowship Brand Premium Men's Grooming Products. Go to the website fellowshipbrand.com. Use the code JBP at checkout. Get yourself some free shipping on your first order of beard oils, balms, and more. My guest today, Lawrence Krauss. He's a theoretical physicist and cosmologist who's previously taught at Arizona State, Yale, and others. He founded Arizona State's Origins Project, now called the Interplanetary Initiative, to investigate fundamental questions about the universe. He's appeared on films, documentaries, television, some of the largest podcasts in the world. He's known for his fascinating books about the universe, like The Physics of Star Trek, Universe from Nothing, which opened up my mind in a lot of ways to the world of theoretical physics. Though I can't say that I totally understand most of the things in it, but I'm tracking. He tries to make it in a way that I can. Also, the greatest story ever told so far. And then his new book that released this year, The Physics of Climate Change. I'm excited to talk about this with you today. Lawrence, I've been a fan for a long time, since I heard you on the Joe Rogan podcast, and I'm so excited that you're joining me today.
Well, it's great to be with you virtually, at least, and I hope we'll have some fun.
Yeah. Hey, so just diving into it at the highest level, you've been doing this for a long time. You're known all over the world as one of the authorities on this subject. What got you interested in the universe? Like, why the universe? You picked the biggest thing, Lawrence. Why the universe?
Well, how could you not be interested in the universe? That's my question I could ask you. I mean, how can anyone not be fascinated? We all are. The point is, most people, everyone is. Everyone looks up at the sky at night when they're a kid or whenever they first become aware of it and are amazed at the enormity and vastness of the universe in which we live and wonder what our place is in the universe. I just get paid to think about it, but everyone else just, most of us think about it, but then we get driven into other areas. And for me, it was, obviously there were specifics, and one of the specifics was that first of all, my mother wanted me to be a doctor, and so she made the mistake of convincing me that, or telling me that doctors were scientists. I got interested in science quite early.
Okay.
Then I read books by scientists and about scientists. I read a book about Galileo when I was about 11. I remember that had a big impact. And I had a neighbor who was an engineer, and his son and I made models of atoms. But books by Albert Einstein, Isaac Asimov, George Gamow, Richard Feynman, those things got me interested in science. And the fundamental aspects of science seemed the most exciting. I think beginning with the book I read on Galileo, who was, trying to understand, who was the first person to see the moons of Jupiter and begin to realize that, hey, that the Earth wasn't the center of the universe. And that whole, I think it romanticized for me the whole process of science, the whole discipline, and in some sense the what seemed to me the bravery of confronting myth and superstition with truth. And so I think that romanticism stayed with me for some time. And then really for me, the most fundamental questions are the most interesting ones. And again, I think they are for most people, but many people just get turned in their life direction into some other direction. But I was able to continue to be able to focus on them, and I feel very fortunate to have been able to do so.
So, I took a very different collegiate path. From a business standpoint, actually, maybe something that we have in common. I did my graduate studies at Arizona State, so it's my former alma mater. But
when was that? Well before I was there.
Yeah, 2013 or 2012, 2013, somewhere around that time.
Oh well, I was there then.
Yeah.
Anyway, yeah. Okay.
So
we ran a lot of Origins meetings, public events. You would have enjoyed them, but anyway.
For sure, I never attended those. Yeah. I would have liked to, but the thing about business college is when you talk about business college, it's like you kind of get an idea what's happening. Somebody's up on the board and they're lecturing about economics or whatever. When I think about what theoretical physicists do, I kind of see a handful of people standing around a chalkboard writing a bunch of numbers and letters and trying to do proofs and things. Like what is it like, not just maybe studying it as a student, but then professing and going into these worlds of uncertainty with mathematics and philosophy? Like, what's that look like? Help the layman.
More math than philosophy. We don't do much philosophy anymore. But I think well, what you science is a cooperative discipline. What most people get this idea because of Einstein, that's sort of done in the middle of the night alone with revelations. And yeah, I tend to work at night, so the details of things I'll work out. And but during the day, it involves a lot of interaction. Indeed, at blackboards, but arguing and discussing, and trying to keep in touch with what's happening in the discipline. That's really a key part of it. And then what you're looking for are anomalies or interesting ideas. The thing about theoretical physics in particular is that it's done in very different ways by different people. It takes all types. Everyone imagines it's sort of some mathematical wizards, and working, as I say, in a notebook. But people do it in many different ways. Some people work alone. Some people work on the same subject for 30 years. Some people, like me, I tend to move around in different subjects and sort of when there's interesting new results, trying to understand them. And part of the time is spent trying to understand weird observations or experiments, trying to understand what those results mean in terms of fundamental theory. And some of it is trying to understand the follow on the past work in understanding the universe, to try and propose new models and new ideas that might be testable in experiments. So there's a going back and forth. Some theorists, some physicists never get near experiments. I have always, well, actually, in the early part of my graduate career, I was quite mathematical, and it took a kind of a jolt before I think it was. There were a number of factors, but a friend of mine, now a friend of mine, then I guess a mentor, Shelley Glashow, won the Nobel Prize in Physics, and was a colleague of mine when I was at Harvard. He at one point said to me, I think in my graduate career, there's physics and there's formalism, and you have to know the difference. And I think a lot of young scientists get wrapped up in the formalism, the mathematics, but really physics is an experimental science, and all science is experimental primarily and empirical. And so I like to try and stay in touch with what the experiments and observations are. And in most of my work, some of my work has been quite abstract and having to do with the nature of weird aspects of the quantum nature of black holes and other things. But on the whole, I've tried to either propose new experiments, predict ideas that could be tested, or explain anomalous results. But but as I say, it's often cooperative. You have to know what's going on. I get a lot of letters. I get letters every day from people who have their new theory of the universe. And the problem is that you really have to be up to date on what's going on to know what the interesting questions are. Which is why, by the way, since you mentioned philosophy, why philosophy really doesn't enter into physics now. Because the philosophy is really useful at the early stages of science when you're framing fundamental questions. But after the science becomes quite mature, as physics is, you're really building on a platform of ideas and experiments of others, and so you really have to be up to date on that platform to really be able to know even what the interesting questions are. And so there's a lot of intellectual baggage in order to get to the point where you can begin to ask questions that might be of interest. Now, it's not always that way, and there's sometimes people come out from left field, and they think, and I get that a lot. People working in their basements that are convinced that they've, just that everything we've done up to now just is wrong. But as I like to say, there's a lot we don't know about the universe, but there's a lot we do know, and you need to have some base in that. So it's been, I remember, sitting at the blackboard, yelling at each other and going up and talk. But sometimes not just a blackboard, just sitting down talking. And sometimes one thinks pictorially about ideas. One thinks about things, tries to get a picture of what's happening. I'm fairly graphical in that way. Before I do the math, I usually try and picture what's going on in my head. But I imagine, it's not, maybe it isn't. I don't know whether it's that different than early stage entrepreneurship. And in fact, I ran a program when I was chair of a physics department once on a master's program in physics entrepreneurship. And the dean of the business school, by the way, you'll be pleased to know, called it an oxymoron, but he didn't realize that.
In what way are they similar?
Well, they're very similar because first of all, physics, as I used to try and tell kids, is about solving problems when you don't know what the problem is. And I think there's a lot of that in entrepreneurships. Also, being willing to use your failures and build on them. One of the things we discovered one of the things we did when I started that program was to bring back physicists who had started businesses and asked what they hadn't been taught. And the answer was how to fail effectively. Because we give students problem sets and things which they're guaranteed to succeed. But in life, in real life, in business, and in real research, sometimes a problem you're working on can't be solved. And you have to understand, the time you've spent on it isn't a waste. You have to say, well, maybe those techniques could be used for something else. And I think it's a lot of that in business too. And it's imagining how to make things work. And in business, you learn very quickly if they don't, I guess.
I love it. I can see it now. That's a phenomenal correlation, and one that I wouldn't have connected that bridge on my own. But thanks for opening up my mind to that.
Sure.
Hey, the next thing I've got here, and I'm like, man, what am I going to ask Lawrence Krauss about? And the thing that I've got to touch on is dark energy and 0 point energy. And this blows my mind. I know they might be separate, but 0 point energy specifically is like something's not moving. It's like the lowest level of non-movement. I don't know. I don't really understand it. Like, if you just take 2 minutes to help I've grappled with this for a while. The definitions online don't make sense. How can I think about this?
They don't make sense.
It's
a hard concept. It's a hard concept. I mean, they're both the same to some extent. So 0 point energy is something that in quantum mechanics systems, the ground state of systems is often not. It often has energy. The lowest energy of a system. I guess the point is this: if you're in a well in a deep trough and you're a classical ball, you kind of roll around and you can go right to the bottom. But in quantum mechanics, as you know, the levels of energy that a particle can have are quantized. You can have certain fixed energies. And the lowest energy state might not be at the bottom of the well. So the lowest energy state you can get into, that the particle can exist in, actually has non-zero energy. Okay? You can't use that energy, you can't extract it because it's the lowest energy state, but it actually carries energy. So quantum systems, even if nothing is happening, can in some sense, if you wish, the ground state, the lowest energy state you're in, when you're as relaxed as you can be, still has energy. Whereas classically, you'd kind of think that you're always relaxed to have kind of zero energy. And the weird thing about dark energy in the universe and why it's related to 0 point energy, and by the way, a lot of crackpots try and make money on 0 point energy and convince people like you to invest in it because they say, wow, if we could just mine that 0 point energy of empty space, look at all, be a new energy source for the world. But the point is, you can't mine it. Because if you could mine it, you'd lower the energy state of the system, right? If I took energy out, the energy state of the system would go down. But if it's the lowest energy state, you can't lower the energy of the system. So it's just you can't mine that 0 point energy. And if anyone tries to get you to invest in such a project, you should walk away as quickly as you can. And I'm not saying that facetiously, because I know NASA has invested money at various times in people's crackpot 0 point energy schemes for propulsion and other things. But anyway, the weird thing about the universe is, and one of the things I kind of recognized early on, I was one of the people to realize this early on, is that it appears that the empty space has energy in our universe. That literally, if you get rid of all the particles and radiation and you just have empty space, it weighs something. And we discovered that because if you put energy in empty space, it turns out to be gravitationally repulsive, not attractive. And when we look out at the universe, we find out galaxies are moving apart faster and faster and faster. And the only sensible explanation of that is that there's energy in empty space. And we don't know why it's there. No one knows, because you can kind of estimate if empty space had energy, how much energy should it have? And theorists like me who come up with that idea in events, the estimates are wildly off from what we see by 120 orders of magnitude. As I like to say, the worst prediction in all of physics is what the energy of empty space should be. And it's the biggest mystery in nature. We don't understand why empty space has energy, but it does. It could be one of two things. It could be there's some field that we haven't yet discovered that stores that energy, and maybe it's going to be useful for something. Or it literally could be the 0 point energy of the universe. And that's would be more akin to what Albert Einstein first proposed. He didn't know it was that, but when he invented something called the cosmological constant, we now understand it would be represented by literally the 0 point energy of space. And one of the challenges for a physicist like me is to say, well, let's predict that 0 point energy of space. And as I say, we can't do that at all. Every prediction we come up with is crazy, which is exciting because we love to be wrong if we're scientists, because it means there's a lot to learn. It means there's something new to understand. So it is the biggest mystery in nature. It's why I spent a lot of my time early on thinking about it. It's why I wrote that book, The Universe from Nothing book. And it's why physicists are kind of fixated. It's such a hard problem, however, that I suspect trying to understand where that comes from and why is not going to be resolved in the near future, even though I like to think about it every now and then.
Okay. Absolutely. I certainly appreciate that. I'm going to have to listen to that a couple of times to like
Yeah, you'll
fully
have to
grasp it.
unpack it. I could have spent the whole podcast talking about it, but we don't have that much time.
Oh,
Otherwise,
for
well,
sure.
but you know what you can do is read carefully my book again.
For sure.
Okay.
Hey, speaking of books, you published this year, again, The
Hmm.
Physics of Climate Change. Let's talk a little bit about it. So what was, this is not in line with
Anyway,
the physics of Star Trek or Universe from Nothing
it's,
or The Greatest Story Ever Told. And your other publications, this is kind of different. What was the catalyst to move into this space? And then, how was it writing the book?
well, it's that's a good question. It is quite different than all my other books, and that's good for me. I like actually. I should make it clear all my books are different, but the others are more related to sort of fundamental science, if you want to call it that, from Star Trek or or the Universe of Nothing. They're all quite different because a lot of there's a great temptation to write the same book over and over again, and I know a lot of people that do that, but I don't want to. So I try and pick with each book I do something that is different than what I worked on before. Sometimes something that requires me to learn something. For my book Atom, which was a biography of an individual atom from the beginning of the universe to the end, I had to learn a lot of geophysics and biochemistry for that too. And so each one is fun and a challenge that way. But this was really quite different, and I don't think I would have written it in normal times. But there were a number of factors. First, it's an issue that I've been thinking about in one way or another because I was chairman of the board of the Bolton the Atomic Scientists for a dozen years almost, the board of sponsors, and the Bolton the Atomic Scientists sets something called the Doomsday Clock, which once a year is sort of updated and talks about how close we are to basically human-induced extinction, if you want to call it that, and primarily about nuclear
Uplifting.
weapons. Yeah, well, it was always depressing those days, but we'd have these symposia where we'd bring in experts, and we used to just look at nuclear weapons. That was what it was created for in the late 1940s, and by Einstein and Oppenheimer. But when I came on the board, we sort of expanded the notion of existential risk to include bioterrorism and climate change, among other things. And so every year we'd have a symposium where we try and get experts to assess the current situation there. So I had kind of a dozen years of tutorials on climate change and had a number of colleagues on the board who I got to know who tutored me. And so it was an area of interest because it's important and because I'm a scientist with some public face. It's important to me, I felt, to kind of um, be able to talk reasonably about it. But what really made it happen was that I led a group on a trip to the Mekong Delta to Vietnam and Cambodia last January, and when I did that, I decided to give some lectures on climate change, and it's like teaching. The only time you ever really learn something is when you teach it, and so that motivated me to do a little more learning because the Mekong Delta is going to be sort of like a perfect storm of climate change because it's so susceptible to sea level change and other things. And 12 million people depend on this delta immediately just for their livelihood, fishing, and more people depend on the richest rice paddy growing area in the world. And a sea level rise occurs by less than a meter, that area can be inundated and it's going to dramatically affect it. So that caused me to really think about it. But then what happened was there was a pandemic, and I found myself for the first time at home, all my travel canceled, the lectures I was giving around the world canceled, and And I knew and I felt, what can I do? I recorded some physics videos because I thought that might be useful. I knew I wasn't a first line responder. What could I do that might be useful? And I thought, well, maybe a book, since this is an important issue, but it's often politicized, a book that's just on the fundamental science of climate change. It doesn't talk about policy, because then you alienate people on the right or left, but just says, what's the science, and can I explain the fundamental science of climate change in a way that people could understand it? And decided I had to be able to do that for myself. And I did something I've never done before. I wrote this book in 12 weeks or maybe 10 weeks. All my other books have taken me at least a year, if not 2 or 3 years. But it's amazing what you can do without any distractions. And I was working 12, 14 hours a day thinking about it. And then it came together. And it's fascinating science. And it's basic science. A lot of people have these misunderstandings about climate change, climate science, that it's based on some tenuous science, but the fundamental science is almost 200 years old. And describing that was fun. And I think writing it as a non-climate scientist is important too, partly because I didn't get involved in some of the jargon that they might, but also, look, this is an issue that's affecting all of us. And almost all of us aren't climate scientists. And if I, as a scientist who is both a scientist and someone who's had experience explaining things to the public, if I can't describe the basic science and the basic predictions of climate science in a way that's comprehensible to people, then how can we have any kind of informed discussion at all? And sound public policy requires having an empirical basis for that policy. So my thought was that this could be the first step in a public discussion, including among legislators, of what the science is, what the minimal predictions are, and then we can talk about policy. So one of the things we're doing, we just, in fact, this week and next week, we're sending 535 copies of this to every member of Congress, hopefully to have some kind of impact. And anyway, it was fun for me, of course, to learn new things, and I learned a lot. And one of the nice things, or useful things, I hope, is that there's lots of figures in here, which I know turn some people off. They don't like pictures or graphs. But a picture is worth 1,000 words. But each of them relates, as I try at the end of the book, to talk about to online sources. So if people are interested, they can go directly online and learn more, which I think is probably the most useful thing. So that's a long answer to your short question.
No, for sure. And I think you touched on an important point earlier, which is the polarizing nature of this particular topic. I think that there are people, and I hate to say climate change deniers, because I don't think that classifies the nuance of that group. I think there's some people who have just really been disenfranchised by kind of bullying and fear mongering and just inaccurate information. And I think that that's frustrating on one side. So it's kind of like writing it off because it feels like there's an underlining political agenda underneath some of these things that's not necessarily tied to common sense or empirical evidence. So it's the second you can prove something wrong, why move forward with it? Then there's another side that doesn't want to hear varying opinions because there's some people that are saying, okay, show me, but show me in a way that I can understand. Show me in a way that's actionable. Like this is the doomsday clock. What can I do as an individual about it? So how do you confront those things in this book?
Well, that you raised some really good points. And in fact, one of the people who wrote a blurb for my book is a friend of mine, Penn Jillette, who's a magician. Penn and Teller.
I'm a big fan of Penn. I met him one time in a Vegas airport. He's taller than I thought.
Yeah, he's very tall, and I'm short, and it's always fun when we're together. But he's kind of known as a libertarian, and some people thought him as a climate change denier. But rather, what he's basically said is, I don't want you to tell me what to do. I want you to give me the information, and let me decide what's useful. And that sort of guided my thinking. And when he more or less said, this is the book I've been looking for, that really made me happy about it. And it's important to critique, in some sense, not just the right or the deniers, but then there's these true believers it's almost like religion. And we hear things from the left which are equally ridiculous. The world's going to end in 10 years if we don't do something. That's not true either. And so I think it's what we really need to show people is that, yes, climate change is happening. There are predictions that are written in stone there are things that are going to happen. There's sea level rise of 0.5 meter at least that's going to take place over the century. The temperature rise of at least 1.5 degrees, and how they can understand where they come from. And then to see that, it's not like a sudden button where if we pass this certain threshold, everything will end. It's a continuum. And the sooner we can begin to address these things, the less likely are the more serious predictions of coming out of climate science. And so you're right, it does seem overwhelming, and people say, what the hell can I do? And the answer is, it's like anything. When I go in the voting booth, I kind of feel like, oh, I'm powerless. What's this one vote going to do? But they add up, right? And I think we all, when it comes to politics, governments rarely lead; they follow. And I think if the public isn't interested in something and to some extent a little bit knowledgeable about it, they're not going to act. And if they're not going to want to act, the politicians are going to act. Doesn't matter what kind of government you have. We saw it in Vietnam. We've seen it in a lot of other places. And so all of us can do one thing. We can begin to at least learn enough to know what the real issues are and what the nonsense is. And we can do some things in our own lives. We can choose to potentially lower our own carbon footprint to the extent that it's amenable with our lifestyle. I happen to now have stopped eating meat, and there are many reasons for that, but one of the reasons is the carbon footprint. It's not. But there are little things you can do. But we all also have a soapbox. We talk to friends. We have friends, neighbors, go to church or your kids in school, and so you can have intelligent discussions about this, and that can be incredibly useful for building a community of interest in this whole subject. So there's a lot you can do without changing the world directly. And literally the way the world changes in the long run is a lot of individuals basically getting interested in something.
So I've got a two-part question here.
Okay.
Part A is, we hear throughout history that there were all kinds of events like ice ages and all these different like changes that have happened to the planet that we inhabit, right? And so, these are either catastrophic events that happened or some kind of like freezing X, Y, and Z. So these things were naturally occurring before cows were farting. So like how do we, or should we might look at that to challenge our belief system if that's what someone believes? And then two, there's graphs in this book about CO2 emissions from 1500 plus years ago. Who's measuring that, and how do we know? Help me look at those two.
Well, that's a fascinating early part of the book. In fact, the fact that we can measure the carbon dioxide concentration not just 1,500 years ago, but 800,000 years ago, and that's the beauty of science. First of all, you're right. There have been long-term changes, and we can try and study those and try and look at their origins. But we can also look at the fundamental science of CO2, and this is what it's very simple. Energy in equals energy out. It's not some profound hidden equation. Energy is coming in from the sun, and the Earth is radiating it into space. If those two numbers are equal, nothing changes. If they're not equal, then the Earth either heats up or cools down. It's basic science. It's high school science. And you can ask, well, what's happening? Well, you can say that if carbon dioxide increases, you can look at the physical properties of it, and you can try and see, and it's very simple as I describe in the book. You can predict that there will be less energy emitted from the Earth, more of it is stored, and since less energy will be emitted from the Earth, it has to go into heating. There's no other place it can go. And you can even estimate from very simple arguments how much you should heat up, as I described. So you can see what's happening, and you can see it's consistent with exactly the carbon dioxide that's going into the atmosphere. And yet, at some level, if it walks like a duck and quacks like a duck, it's a duck. But more importantly, we can, as I say, try and test our models by going back over a long time, because yes, we've only been measuring carbon, and it's carbon in the atmosphere, carbon dioxide, and it's been a wonderful thing, happened by serendipity, as I describe in the book, starting in the 1950s, by Keeling. But since the late 1950s, every single day in Mauna Loa and in the Antarctica, we measure the carbon dioxide in the atmosphere, far away from industry and far away from other things, and have seen this remarkable fact that in the last 60 years, the carbon dioxide content of the atmosphere has increased by 30%. But what we can do is, it turns out we can look back in history before we were directly measuring it by looking at other records. And one of them, it turns out, is ice cores in Antarctica and in other places, but in particular in Antarctica. Because every year Snow falls in Antarctica, and when the snow falls, it traps air bubbles, right? And then it gets compacted. And then you have the next year, and it's kind of like tree rings. You can measure, you can actually count the years back. And by looking at the bubbles in that ice and measuring, you can measure directly the carbon dioxide content of the atmosphere at the time that ice was formed. And you go back far enough, as I said, we can now go back to 800,000 years. And what's nice is you can match it on to the measurements that were made in 1958, and they match on perfectly. And that gives us a record. It turns out you can even measure the temperature at that time. You might say, how the hell can we do that? There weren't thermometers. But it turns out the way different isotopes are deposited, oxygen and is one example, comes in a variety of isotopes, and certain of them preferentially rain out before they, from the water because they're heavier, and if you want to call it that. And so you can look at the isotopic ratios of different heavy isotopes of oxygen and other elements, carbon and other things, and it turns out it's temperature dependent, right? Because the more energy you have to pull these things out and hold them in the atmosphere, it'll cause a different variation in their precipitation. And so you can measure the abundance of these different isotopes, and that gives you a measurement of the temperature. It's pretty cute. It's pretty neat, as I described there. And it's amazing we can do it. And then, of course, you have theory of how the atmosphere works and how the Earth's orbit around the sun works. There's periodic long-term variations in the Earth's orbit of the sun. Milankovitch cycles are called, and you can see how the Earth is varying. Well, that's what makes it scary, because you can measure that these variations, sure, over 10,000 years, these variations, but the carbon dioxide abundance during the last 800,000 years has never come close to within 30% of what it is now. It's never risen as dramatically over such a short time, which means that we're in a new stage of the Earth, and means that there are a lot of unknowns, but the fact that there are a lot of things we don't understand, as I said before, doesn't mean there's nothing we do understand. And so there are uncertainties, but there are some things we can say with great confidence. And then what's important, and I know there's a book coming out next week by a colleague who's more or less saying that the uncertainties mean we shouldn't, that our public policy shouldn't be based on worries about climate change. And I'm very concerned about that book, because I think it misrepresents the situation. The fact that there are uncertainties, and we know the uncertainties in our predictions, should motivate us to do more. Because in the variation of, say, at the end of this century, you can see models that'll say the temperature of the Earth is 2 degrees higher. There are ones that make it 8 degrees higher. Well, the good news is if it's only 2 degrees higher, then there'll be limited impacts. But the fact that we have an uncertainty, and it could be 8 degrees, which would produce dramatic impacts, including the melting of the Greenland ice sheet and other things, means, as I was just saying in a piece I wrote, it reminds me of Dirty Harry in those movies, if you remember Clint Eastwood, when he'd have his gun and he'd look, he didn't know if there were bullets in his gun. He'd say, "Now you got to think, punk. Are you feeling lucky?"
Yeah.
And the question is, are we feeling lucky? Yeah, maybe we're feeling lucky. Let's not do anything. But the fact that that might happen should suggest to us that maybe if we can do it in a way which doesn't hurt our economy and maybe even helps our economy, given the uncertainties and the possible risks, we might want to even claim that those uncertainties should suggest that we act even more dramatically than we would otherwise. So I think that's important to recognize. And uncertainty is not a bad word in science. It's a good word. It's probably the only area of human activity where you can really explicitly quantify what you don't know. And that's important.
That's a beautiful thing. And I know you're tight on time today. I certainly appreciate you spending this much time with me so far. One more thing is we're closing out here. Your favorite thing about going through this process, something that you didn't expect to learn going into it, or expect to learn about yourself as you time collapsed your writing journey.
Well, I learned a lot about myself. I learned if I reduce my my commitments, like doing podcasts like this, then I could do a lot more work. That's the first thing. It was really true. With no commitments, I was able to do a lot more. I was able to work much more efficiently. But for me, I have to balance those things. So I think it's important to reach out. But there were a lot of things that surprised me. And that's what I love about writing a book or any research, as I'm surprised. And that's the whole point of doing it. If you knew the answer before you did it, it wouldn't be any fun. So being surprised and learning that your misconceptions are misconceptions is exciting. Um, I learned that, the greenhouse, I never really thought about, but the greenhouse effect really has very little to do with greenhouses. And the whole notion of why greenhouses get hot is different than the reason the Earth is getting hot. The fact that this effect of climate change warming isn't really, what's really important is not what's happening on the ground, but what's happening at the very top of the atmosphere was surprising. And then certain numbers, like the fact that the world's oceans have increased in temperature by 0.07 degrees Celsius over the last 20 years, which doesn't seem like a lot, but the oceans are pretty big. And if you ask how much heat did we have to put in those oceans to make that water temperature increase by 0.07 degrees, it's the equivalent of 3.4 billion Hiroshima-level atomic bombs over the last 25 years.
Wow.
4 every second, 24 hours a day, 365 days a year for the last 25 years. That's a lot of heat. So anyway, there are lots of things that are fun to learn. Little things like the fact that actually a lot of this was known in the 1880s. And one wonderful geoscientist I'd never heard of did an amazing estimate of what, because people sometimes say, how can humans impact the atmosphere? The Earth is so grand, how can we do it? If you take the carbon dioxide abundance that was 1900, about 300 parts per million, but you just ask, if you solidified it all or liquefied it all and put, how thick a layer on the surface of the Earth would it be? 1 millimeter. And he said, well, 1 millimeter is a lot less than the layer of life on Earth that's manipulating carbon. So maybe life can actually affect the carbon dioxide abundance in the atmosphere. And of course, as humans, we've not just been exploring the history of life over the last little while. We've been going down where the dinosaurs were and extracting the oil for millions of years. So it's not surprising that we can dump a lot more carbon into the atmosphere than nature can on a regular basis. We dump about, let's see, 0.03, 1, 2, about 300 times, at least 300 times more carbon in the atmosphere from human industrial activity than all the volcanoes in the world do on any given year. Anyway.
So where are you most active today, either on social media or otherwise? And then where is the best place to pick up your book?
Well, it depends on your predilection. I know Amazon sells it. Some people don't like Amazon. They're selling it at a discount right now. There are lot that you can go online and get it from a lot of booksellers. If your local bookseller isn't selling it, you should go to them and say, "Why aren't you selling it?"
There you go.
But and it's also an ebook, which is nice. And I'm not, people, you might say, well, they're good. That's better for the environment. But of course, there's a lot of hidden issues about that, right? In energy consumption in cloud storage and things like that. But the ebook is available. And I did an audiobook, which I read too. So all of those are available on Amazon and other places. There are a lot of places you can actually find me online. I am active on social media at Krauss1 and you can read most of my pieces or my videos online. One of the areas I'm most active and very excited about is that I'm leading both a nonprofit foundation called the Origins Project Foundation and an associated podcast which it runs called the Origins Podcast with Lawrence Krauss, and it's been really exciting and fun, and we've had a lot of interesting guests ranging from Ricky Gervais to Noam Chomsky to Nobel Prize winning physicists. And it's and we go in depth on these issues, and in fact, including climate change, among other things. And so I try and mix science and culture there. So I really want to encourage you to do that. And the foundation is really about trying to bring people, as we're doing today, to bring people to talk about the most interesting ideas and things that affect society in the 21st century, and to connect science and culture. So both of those activities are things I'm excited about. And the Origins Project Foundation has a webpage called originsprojectfoundation.org. Podcast, you can go to YouTube, or Patreon or iTunes and all those things. And then I'm continuing to write, and when I get mad I write in things for newspapers. I just finished a few pieces, one for the Wall Street Journal. We'll see what happens. And I'm actually working on another book, and distractions notwithstanding.
I love it. I love it. Well, I will put links in the podcast episode to all those things that you just outlined there, being the Origins Project Foundation, your podcast, supporting it, and then links to your website and some of your social and work as well. So again, sir, thank you for making some time for me on the podcast today. I loved just being able to scratch the surface of your mind, and looking forward to the next time we get an opportunity to chat.
Yeah, well, it was itchy, but now thanks for scratching it. But
You're
anyway,
welcome.
no, anyway, I'll keep letting it be itchy. I think it's best. But okay, you take care. Thank you very much.
All right. Cheers. Bye.